oscillator. So before that, so we'll see about today topic is oscillators. Oscillators. So if you want to define an oscillator, otherwise if you want to discuss about oscillator, what is an oscillator, all these things we'll see here first. So if you take an oscillator, oscillator is an electronic circuit which is associated with a transistor that provides an alternating output while deriving its input from direct current source. Okay, so that means oscillator is nothing but it is a device which will be which will be converting a direct current to AC. Direct current to AC. So oscillator is a device which converts DC into AC. Therefore, this oscillator is also known as we can call it as an inverter. We can say that we can call it as an inverter because it is converting DC into AC. So this is what we have about oscillator, and oscillator generates alternating voltages or currents over a wide frequency range from a few cycles per hour to millions of cycles per second. It is going to be generated. So the oscillator is an essential part of this radio communication system and finds its use in radio and as well as the TV transmission and receivers. It is having so much use. Okay, so the function of an oscillator is similar to that of an amplifier. However, there is a basic difference between an amplifier and an oscillator. If you take an amplifier, it produces an output signal whose waveform is similar to the input signal, but whose power level is generally high. Suppose if you take an amplifier, so if this is an amplifier, if you are having, this is an amplifier. So we will be giving input to this an amplifier, and you can expect output in this amplifier. So in the case of the amplifier, suppose if you take any signal, say that which is having, this is the signal which you have been given as input. So in the output, we are going to be expect a higher magnitude. That is nothing but the power, it is going to be increased. So that is what an amplifier it is going to be have. Okay, an amplifier which can produce an output signal whose waveform is similar to the input signal. So if you see here, this waveform and this waveform, these two are similar, you are going to be have. But the thing is, here the power in the output, whichever it has been generated, this power level is generally high, you are going to be have in the case of the output. So that is what we call it as an amplifier. So generally, in the case of the oscillator, this additional power is supplied by the external DC source. External DC source. Thus, an amplifier, the frequency waveform and magnitude of the AC power generated is controlled by an AC input signal. So, if there is no input signal, there is no output signal, and hence there is no energy conversion. If you take on the other hand of an oscillator, if you consider the frequency, waveform, and magnitude of the AC power generated is controlled by the circuit itself, and it does not require an external signal either to start or maintain energy conversion process. So thus an oscillator is an amplifier which provides its own input signal. So in the case of this amplifier, we required a separate input signal is required so that we will be getting a high output signal. Whereas if you take in the case of an oscillator, so which is not required an input signal, it is going to be produced on its own. So we can say that oscillator is an amplifier only, but which is providing its own input signal. So it keeps producing an output signal so long as the DC power we will be connected here. So if you take, if you see here as we have seen here, so an amplifier and as well as the, we'll say oscillator, both block diagrams I'll draw here. So here, so this is the signal input we are going to be given. Signal input will be there as it is an amplifier. Signal input will be there, and you will be connected to certain DC power source. DC power source will be connected to an amplifier, and you can expect the output signal, which we call it as a signal output here. So this is in the case of the amplifier. Suppose if you take consider an oscillator, if you consider, so in the case of an oscillator, so here we have an oscillator. This is an oscillator. So we will be connected one DC power source to this one. DC power source. Here we are going to connect. And here we can expect signal output. Okay. So this is an amplifier. This is an oscillator. In the case of the amplifier, if you see, we have connected input signal as well as the DC power source. Both we have connected, and we can expecting the signal output in the case of the what we call amplifier. Whereas if you take this oscillator, if you consider in the case of the oscillator, we are going to connect one DC power source. We are going to be connect, and we can expect a signal output. So in the case of the oscillator, the input signal for this oscillator is provided by itself. So that is what we have the difference. So we can say that amplifier is required as some input signal, whereas in the case of the oscillator, we don't require any input signal. We can get directly output signal we can get by its own we have. Okay. So that is what the difference between this amplifier and oscillator you are going to be have. So if you see next different types of oscillators, if you see, so otherwise we can say that what are the essential things which we required in the case of the oscillator. So what are the essentials of transistor oscillator, essentials of oscillator, or essentials of a transistor oscillator you are going to be have. So if you take an oscillator, you required two minimum of things which we required, three different things which we required. One we call it as a tank circuit. Another one we have the transistor amplifier, and then we have the feedback circuit. So these are the three things which will required the case of the oscillator. So first one, what we required is we required a tank circuit. What is that? Will explain. Tank circuit is required, and as well as we required a transistor amplifier or simply an amplifier, which is constructed with the help of is what we call a transistor. And then we required another one, that is a feedback circuit. So mainly the case of the transistor, these in the case of the oscillator, these three things which we require. So if you draw the block diagram for this one, so these three, we'll see here how the block diagram will be there. So here, this is an inductor, this is a capacitor which will be connected, and this is a amplifier. Otherwise, you can say that transistor amplifier, and we have a like So this will be connected to a tank circuit here. So like this is what we call it as a feedback circuit. What is feedback already might be learned. So this will be given as a input for this one. Okay. So if you observe this block diagram, so these are the essential of an oscillator, which is consisting of three different things we have. Like one is a transistor amplifier is there, one is a feedback circuit is there, and another one is we call it as a tank circuit. So this tank circuit is going to be depends upon the type of oscillator. Here we have shown like the case of L and C. Suppose if you study, if you talk about what is tank circuit, so first, we'll see what is a tank circuit and all those things. So if you take a tank circuit, so generally it is consisting of an inductor coil. So that is represented with L, which is an inductor coil you have, and it is connected in parallel with an capacitor. So this is connected in parallel with the capacitor C here. So it is connected in parallel to capacitor. So the values of these inductor and as well as this capacitor, which we call it as a components, which determines the frequency of oscillation of the circuit, it is going to be determined. And the second one, which we have is an transistor amplifier. So here this transistor amplifier, which changes the this DC power, okay, DC power received from the battery into AC power. Okay. So generally DC power already we have seen that in the previous one, which will be connected in here. So this DC power, whichever it has been got for an amplifier, it is going to be take the DC power and it is going to be convert into AC power, and it will supplies to the what we call a tank circuit to meet the losses. So this is the function of the what we call a transistor amplifier we have. And the third one, which is having feedback circuit. So feedback circuit is nothing. What is feedback is some part of the output is taken into the input, then we call it as a feedback here. So generally in the case of this what we call oscillators, we are going to be use positive feedback you are going to be used. So that is so already we have, you might be knowing that there are two types of feedbacks, that is positive feedback as well as the negative feedback. Generally, the feedback which we use in the case of the oscillators is positive feedback you are going to be have. So here, this feedback circuit, whichever we have, so this feedback circuit, it provides generally positive feedback it is going to be provide. So positive feedback you are going to be have. So it supplies a part of the collector energy to the tank circuit uh, in what we call tank circuit in correct phase to maintain the oscillations you are going to be have. So these are the three things which we required in order to construct an oscillator you have. So these are the three things which we required for an oscillator you are going to be have. And then we just will see what we call different types of oscillations. That is nothing but uh, classification of oscillations if you see. So how they have been classified. Classification, classification of oscillators. How they have been classified, we'll see here. So oscillators mainly, otherwise broadly, can be classified into three categories. You have three categories. One which we have as depending upon the method of producing oscillations, that is nothing but what type of oscillations it is producing in the output. So depending upon the method of producing producing oscillations. So what type of oscillations it is producing, depending upon that one, when it has been classified, and depending upon the waveforms of the generated, depending upon the waveform of the generated voltage So this is one type of we can divide in oscillations, and the third one which we have is depending upon the frequency of generated voltages, depending upon the frequency of generated voltages. So these are the three types of classification broadly it has been done. So the first one which we have is here we'll see about what is uh, how it has been classified. So here we have a first one. So under this first one, which we called it as depending upon the method of producing oscillations, we have been classified. So this classification mainly depends upon the particular device that makes oscillations possible. So according to this method, oscillators have been subdivided like what we call feedback oscillators, that is nothing but positive feedback oscillators, as well as the negative resistance oscillators we have. So in the case of the feedback oscillators, in a feedback oscillator, a portion of the output voltage is fed back into the circuit in a proper phase. So generally positive feedback you have such positive feedback we have such that it is equal to the original input signal of the amplifier you have. So the amplifier then provides its own input and becomes an oscillator. So thus an oscillator is an amplifier which obtains its input not from separate AC source, but by positive feedback from its own input. So accordingly, an oscillator is a positive feedback amplifier whose voltage gain is infinite you are going to be have. So this is one type we have under this depending upon the method of producing oscillations. And another type which we have is the negative resistance oscillators. So in this case, if in a circuit that currents decreases with increasing the voltages, the circuit is said to have negative resistance. Okay, so the current is going to be decreases with the increase in voltage. So the circuit is said to have a negative resistance. So oscillators based upon this principle are called negative resistance oscillators. We are going to be called. Okay, so this is one type we have. And second type of oscillator which we have been classified depending upon the waveform of the generated oscillators. So under this, mainly this we are going to be study here. Under this also the some subcategories it has been divided. One is which we call it as a sinusoidal oscillator. Sinusoidal oscillators you have, and another category under this which we have is non-sinusoidal oscillators. Non-sinusoidal oscillators. These also comes under this only. So these non-sinusoidal oscillators are also called it as uh, what we call relaxation oscillators we are going to be called. So under this sinusoidal oscillator only we are going to be studying mostly. So under this we have like a Hartley oscillator, Colpitt's oscillator, crystal oscillators, as well as the RC phase shift oscillator, RC oscillators. So mainly RC oscillators comes under this, as well as the LC oscillators. You are going to be get under these sinusoidal oscillators. So in the output, the waveform which we are going to be get in the case of the sinusoidal oscillator is a sine waveform which we are going to get. So this is the output which we get in the oscillator, which we call it as a sinusoidal oscillator. And coming to this non-sinusoidal oscillator. So in the case of the non-sinusoidal oscillator, the output waveform of the these oscillators is marked as non-sinusoidal. That means other than sine waveform, they are going to be have. Okay. So under this, you are going to be get different types of multi-vibrators. You are going to be get multi-vibrators under this non-sinusoidal oscillator you are going to get, and as well as the some blocking oscillator we are going to be called. So this also you are going to be get what we call under non-sinusoidal oscillator. Blocking oscillator you are going to be called. So in the case of this non-sinusoidal oscillator, the waveform whichever it is going to be produced in the output, maybe you may have the what we call square waveform you may have in the output. Otherwise, you may be having the rectangular waveform in the output you are going to be have. Otherwise, you may be having the sawtooth waveform. So this type of waveform you can expect in the output. And one more type of waveform which we have is a triangular waveform. So this also you can get. So these all comes under the non-sinusoidal oscillator, and as well as this we call it as a multivibrators you are going to be got. So this is one type of classification which we have seen. And third one is what we call it, depending upon the frequency of generated voltages. So generally in the output, whatever may be the frequency which they are going to be produced, uh, we are going to be measure. So generally what type of frequencies it is going to produce in the output is it is going to be produce oscillator is going to be produce audio frequency waveforms, which we call it as a AF oscillator we are going to be called. So under these the frequencies in the range of 50 hertz to 20 kilohertz you are going to be have. So 50 hertz to 20 kilohertz, in between this range audio frequency you are going to be have. And one more type of under this what we call, depending upon the frequency of generated voltages, another type which we have is a radio frequency wave oscillator. Okay, so radio frequency which we call it as a RF, radio frequency oscillator we are going to be called. So these oscillators generates voltages of the frequency of you are going to be have beyond this 20 kilohertz. So the range will be 20 kilohertz to and 30 megahertz. So in this range you are going to be have radio frequency oscillators. And one more type of oscillator which we comes under this is ultra high frequency oscillators we are going to be called UHF, ultra high frequency oscillator we have. So under this ultra high frequency oscillators, these are also known as a microwave oscillators, and they generate high frequencies which are having greater than 30 megahertz, greater than 30 megahertz. So this is for a classification of what we call oscillators we have. So one depending upon the method of producing oscillations, second one depending upon the waveform which is generated, and third one depending upon the frequency which is generated we have. These are the three broadly classification of oscillators has been done. Okay, so next we'll move to another topic which is a criteria which is known as a Barkhausen criteria for oscillations, otherwise Barkhausen Barkhausen criteria, Barkhausen criteria for oscillations. So this is very important, Barkhausen criteria. In order to maintain sustained oscillations, we require this one. So in this one, draw circuit diagram here. Right. So this is amplifier with the gain. and we have as well as feedback network. Feedback network we have. So here you can expect output. And some part of it will be taken as an input for this feedback. And again, this will be given the input for an amplifier. So in this block diagram, otherwise we'll see here. So what is Barkhausen criteria? So to obtain the condition for sustained oscillations, so here we considered a feedback amplifier with gain A we have been considered. We have considered a feedback amplifier with the gain, voltage gain generally we'll call here. Voltage gain A we have been considered. So let we consider a EG. EG be the input voltage and E naught, this EG is input voltage and this E naught will be the output voltage we have. Okay. So if the feedback network introduces a fraction beta of the output to the input here, okay. So this feedback network which is going to produces a feedback fraction of beta. So then we said that EG is the input voltage and E naught will be the output voltage. So here we have E naught is the output voltage. So this will be some part, it will be taken as a input here. So so here beta is nothing but it is the feedback fraction which is introduced of the output into the input. So then the feedback is positive here. The voltage appears at the input of the amplifier will be here EG plus beta V naught you are going to be having. This is what actually the input which is going to be appear at the input. Now, if the amplifier whichever we have taken, this is amplified A times the amplifier to give the output E naught. So then we can say that this E naught is equals to EG plus beta V naught into it has been amplified by how many times? A times. So the final output here it will be E naught is equals to EG plus beta V naught into A you are going to be have. So how we have got it here it is this is some part of the output is taken back into the input which is through feedback network. So beta fraction if you have been taken. So therefore beta sorry it will be E naught. We have taken it as E naught not V naught. So beta E naught here beta E naught. Okay, so this beta E naught will be given again at this point if you have been given. So already we have an input signal at this point is EG is the input voltage we have been got. So the amplifier circuit is going to be have total input will be EG plus beta V naught is the input for EG plus beta E naught is the input. So therefore the output voltage which we can expect at the final oscillator will be E naught that is equals to EG plus beta E naught into A you are going to be have. So now if you want to get this EG value here, what actually we are going to be given here. So it will be E naught plus EG into A plus uh, A beta E naught you are going to have just multiplied here. Okay. So therefore EG A is equals to this. If I take to that side, E naught plus A beta E naught you are going to be have. Therefore, this will be equals to EG into A is equals to E naught if I take common. So it will be 1 plus a beta you are going to be have. So from that, Eg is equals to E naught into 1 plus a beta by a you have. Okay. Eg, EGA, sorry, here it is plus now. Plus Eg plus a beta E naught. This is also plus. So now it becomes minus EGA is equals to E naught. EGA is equals to E naught minus a beta naught. 1 minute. So now this is so EGA is equals to E naught here, and this we will take to this side, it will be minus a beta naught. So now EGA is equals to E naught. If I taken common, it will be 1 minus a beta, as well as here also it will be E naught into E naught into E naught into 1 minus a beta by a here. So we have got Eg is equals to E naught into 1 minus a beta by a we have. So here if you consider that if a beta value is equals to 1, that here if you take a beta is equals to 1, then what will happens? So this will becomes a 0. That means Eg value becomes a 0. Okay. So what actually Eg is nothing but input voltage. So here Eg is equal to 0 means an output voltage is obtained without any input signal. So here effectively the Eg value is 0 from this equation. If you consider that if A beta value is equals to 1, then Eg value becoming 0 here. That means an output voltage is obtained without any input signal. So then the amplifier functions as an oscillator. So therefore, this condition for the maintenance of oscillations. So this condition, if A beta is equals to 1 is the condition. Otherwise, beta A is equals to 1, which we have. Beta is equals to 1 by A, we can say that 1 by A. So this condition for the maintenance of oscillations is A beta is equals to 1 or beta is equals to 1 by A. So this equation, A beta is equals to 1 or A beta is equal beta A is equals to 1, whatever it may be, is known as Barkhausen criteria. It is known as Barkhausen criteria for sustained oscillations. Barkhausen criterion for sustained oscillations you are going to be got. So under this condition, what we are going to be have is if A beta is equals to 1. So generally AF is equals to A by 1 minus A beta. So which is equals to infinite, because A beta value is equals to 1. So its value is equals to 1. That means there is there is an output without any input signal. That is an amplifier will working as an oscillator. So this is very important. So which is known as a Barkhausen criteria for oscillations you are going to be called here. Okay. So next we'll move to so now we'll move to another topic. So now we'll see about one type of oscillator which is known as a Hartley oscillator. 1 minute. Okay. So here we'll see about Hartley oscillator. So here we'll draw the Hartley oscillator. So this is the transistor, three terminals of the transistor. This is the base. This is the collector which we have. This is the emitter. So C configuration transistor. So for this transistor, so collector is connected with a RFC choke, RFC, and this input dividing resistors we have. So this is R1. So this is VCC, which is plus VCC you have. And here for this emitter, we have been connected one resistor and another capacitor has been connected to this one. And this dividing resistor here, it is connected to this one. So this is the resistance R2 here. And this will be connected to the ground generally. And this feedback circuit should be there. So in the output capacitor, so this comes, and here we have two inductors. And this is the input capacitor here we have. So this is the first capacitor, C dash will take. This is another capacitor, C double dash. So these are the two resistors, R1, R2, and this is the emitter resistor, RE, and this is the emitter capacitor, CE, and this is one inductor L1, another inductor L2. So this is in parallel capacitor is connected. Generally variable capacitor, C you have. So here at point 1, this is a second, the third node we have, the second node which we have. So this is the circuit diagram of Hartley oscillator which we have. So now we'll discuss about the circuit diagram, then we'll move to the what is the frequency of oscillations which we can obtain here. So here, in the case of this Hartley oscillator, as we have drawn here circuit diagram, so a circuit diagram in which we have the resistors like R1 uh, resistance, R2, and as well as the RE. These are the three resistors which we have. So, and these resistors R1, R2, and RE, and the power supply whichever we have here, it is a plus VCC and power supply VCC. These resistors R1, R2, RE, and the power supply VCC will establishes the DC operating point to the transistor. So these resistors as well as the plus VCC, they establishes operating point. They establishes the operating point to the transistor. To the transistor, they are going to be established the operating point, right? So then after establishing the operating point to the transistor, the frequency determining network here, it is made up of a variable capacitor C here. Here it is made up of variable capacitor C and the inductors L1, comma L2 here. Okay, so the frequency determining network is made up of variable capacitor C and the inductors L1 and L2. Okay, so here the coil L1, that is nothing but the inductor, is coupled with L2, and this combination forms an auto transformer. L1 is coupled with L2 here, as we have seen here. L1 is coupled. This is the L1, it is coupled with L2, and this L1 coupling inductively coupled with L2, and this combination is going to be formed as an auto transformer here. And the remaining capacitors which we have is a C dash and C double dash. So this C double dash capacitor, whichever we have, so this C double dash capacitor, it will blocks DC signal, and it will allows AC signal to the what we call tank circuit or frequency forming circuit. Okay, double dash blocks the DC and provides AC path from the collector to the tank circuit. And we have one more radio frequency choke, which we call it as a RFC. So this RFC provides a DC load for the collector and also prevents AC from reaching the DC power supply, VCC. So then after we have one more capacitor, C dash here. So this C dash capacitor and resistor R2, whichever we have, produces self-biased base voltage with capacitor CE, which provides AC ground and prevents any signal degeneration here. C also provides some temperature stabilization also, it is going to be produced here. Now we will move to the circuit operation here for this Hartley oscillator. So in the case of the circuit operation for the Hartley oscillator, so when the collector is connected with the supply voltage VCC by closing switch S here, so the collector current starts rising and charges the capacitor C here, charges the capacitor C. So when the capacitor is fully charged here, it discharges through the coils L1 and L2, that is the inductors L1 and L2. So setting up damped harmonic oscillations in the tank circuit here. So the oscillatory current in the tank circuit produces an AC transistor and appears in the amplified form in the collector circuit. Now this feedback of energy from the output to input, that is output is nothing but the collector emitter circuit and the input is nothing but a base emitter circuit. So this feedback energy from the output to the input is accomplished through auto transformer action. So here the energy is fed back into the circuit by means of mutual inductance L1 and L2. So this energy supplied to the tank circuit overcomes the losses occurring in it, and as well as the uh, consequently the oscillations are sustained in the circuit you are going to be have. Now here it may seem that the energy supplied to the tank circuit is in phase. It is in phase with the generated oscillations here. So the ends 1 and 2 here. So these ends 1 and 2 of the auto transformer, that is ends of the 1 and 2 is nothing but L1, L2 combinations you have. So this end 1, this end 2 here, whichever we have, they forms auto transformer. So this is going to be 180 degrees out of phase. It is going to be 180 degrees out of phase. That is nothing but L1 and L2 are 180 degrees out of phase. Now here the terminal 3, whichever we have is this earth, it will be at zero potential. So now when this one is at positive potential with respect to this terminals 2 and 3 will be at negative potential with respect to 3 at the instant. So suppose the phase difference between the voltages across L1 and L2 is always 180 degrees. That is nothing but the phase difference between this L1 and L2 will be always 180 degrees. So this is the 180 degrees of phase shift is provided by these inductor coils, and the remaining 180 degrees of phase shift, it is going to be remaining 180 degrees of phase shift, it is going to be produced with the help of this what we call a BJT, that is nothing but a transistor. So 180 degrees of phase shift is provided by these two inductors L1 and L2, and the remaining 180 degrees of phase shift is between input and output voltage by the transistor itself. So therefore, this 180 plus 180 total phase shift of 360 degrees, 360 degrees are 0 degrees is going to be making feedback positive or regenerative, so which is essential for oscillations. So consequently, otherwise the continuous undamped oscillations you are going to be get here. Okay. So this is what the circuit operation you are going to be have. And if you want to take the mathematical analysis of this one, so we can make a equivalent circuit for this previous circuit diagram here. So whichever we have drawn here. So for this one, we are going to be make equivalent circuit. So which we will draw here. So here we have equivalent circuit for this one. So this will become Z1. This will be Z2. This is Z3 here. So this is HA. And the terminals here, it will be first terminal. This will be the second terminal, and this is the third terminal, which is grounded at this point. The current flowing will be IB into this. The current is I1, which is flowing here, and here it will be I we have. So this is the equivalent circuit for the circuit diagram whichever we had drawn. So it will representing the inductive or capacitive reactance of an oscillator, Z1, Z2, and as well as the Z3. Z1 and Z2, Z3 are representing the inductive or capacitive reactance of an oscillator. So we may draw this, we have drawn this simplified equivalent circuit of oscillator as shown here. We have drawn here. So here the feedback source of EMF will be HRE V0, which has been omitted because we have been neglected this one, because the reverse voltage HRE, whichever we have of a transistor, is negligible. And similarly, the output resistance 1 by HOE is in parallel with the Z2 we have, which is large. So therefore, it has also been omitted. So this is also we have been neglected. This also has been neglected here. So since the input resistance is HIE, which we have drawn here of the transistor, and impedance Z1, this HIE and impedance Z1 are in parallel. These two are in parallel, and their equivalent impedance value is given by Z dash. So which we can write it as 1 by Z dash plus 1 by Z1 plus 1 by HIE. So if you solve this one, so it will be Z1 plus HIE by Z1 HIE it becomes. So this is the equivalent impedance. So if you want to get here from this, we get it as Z dash is equals to Z1 HIE by Z1 plus HIE you are going to get here. So this is one we are going to get. Then after this equivalent impedance Z dash is in series with Z3 we have, in series with Z3 we have this combination. So this combination will be acts as in parallel with the Z2. So therefore the load impedance ZL between the terminals 2 and 3 here, the load impedance between the terminals 2 and 3. So actual circuit which we have here, here this one, between this 2 and 3 here, load impedance, which we are going to get it as here, okay, which we are going to get it as load impedance as 1 by ZL plus is equals to 1 by Z2 plus 1 by Z dash plus Z3 we have. Z dash plus Z3 we have. So now Z dash already we have seen. So Z, this is ZL. So this, if you, so by substituting all the values, if you solve, we get ZL is equals to like a Z2 plus Z2 into Z1 Z3 plus HIE and Z1 plus Z3 divided by, you'll get it as a HIE into Z1 plus Z2 plus Z3 plus you'll get it as a Z1 Z2 plus Z1 Z3. So this is Z1 and this is Z2 Z1 Z2. So this is ZL value we are going to get. So from this, if you calculate what we call output voltage we get, and as well as the beta fraction you are going to get, beta is nothing but that is a feedback fraction which we can get. Then after, by substituting the A beta value, so we can get the conditions for oscillations as we are going to get it as omega in terms of omega, we are going to get omega is equals to 1 by, we're getting in the form of root of L1 plus L2 plus 2m plus C you are going to get. And finally, this omega is nothing but a 2 pi f angular frequency. So from this frequency of oscillations, we can write it as omega by 2 pi we can write here. So if you write this, we can get it as 1 by 2 pi under root of L1 plus L2 plus 2m into C you are going to get here. So this is nothing but the frequency of oscillations. Frequency of oscillations upon the Hartley oscillator, you are going to get it as F is equals to omega 1 by 2 pi under root of L1 plus L2 plus 2m into C. So similarly, condition for sustained oscillations we can solve here, so that we can get it as HFE is equals to, we can get it as L1 plus m by L2 plus m. So this HFE will gives the what we call condition of sustained oscillations in the case of the Hartley oscillator you are going to get. So this is what the Hartley oscillator which we have. Okay. So now, as of now, we'll stop here. This is the condition for a Hartley. We have seen about the Hartley oscillator. So we'll stop here today.